Okay, so let's just take a look at oxidation states and oxidation numbers again for a couple of minutes in case you're having any issues with doing the oxidation number homework, okay, the questions. So the other day in class, Thursday, we talked about the fact that really these are the same thing. It's just the number is what's assigned to represent the state, okay? And the reason we use oxidation numbers and oxidation states is to help us figure out what what entity in a reaction is going to be oxidized and what entity is going to be reduced. Okay, so it helps us look at, is it gaining an electron or losing an electron? Now, some things automatically have a number. If they're ions, then they have a charge. But it's the things that don't have a charge that can sometimes get confusing. So that's why we use these oxidation states. Okay? Now, we already talked about the role that electronegativity plays in here. And sorry, my periodic table is different. I have 12,000 on my desk at school, and I didn't bring any of them home. Don't tell Mr. Jewett, because I don't have a pocket one. He'd be so disappointed. But remember, we have the oxidation or the electronegativity numbers here in the periodic table. For you, it's right here below the atomic number on the periodic table you have. And the bigger the electronegativity, then the one that has the bigger electronegativity is the one that's going to be given the credit for having the electron. Okay? So we'll come back and talk about electronegativities as we're going through what's the oxidation number for different atoms and ions. Okay, so there are a few rules here. Anything that has a zero charge, anything that's in its element form, it can be a diatomic or just a pure element. So it could be O2, it could be H2, it could be copper, it could be aluminum. All of those things are going to have an oxidation number assigned to them of 0. Hydrogen is almost always positive 1. Okay, so it rarely holds on to the electron when it's interacting with something else. The only times that it does is right down here. Hydrogen has an oxidation number of -1 when it's bonded to things that are less electronegative. And if you look on the periodic table, that would be these two dudes. Okay, so whenever hydrogen's bonded with anything in these first two columns, it's going to end up with an electronegativity or an oxidation number of -1. In all other cases, it will have a +1, unless it's H2, which means it's pure hydrogen, and so then it's back up here, it's 0. Okay? Oxygen almost always has an oxidation number of -2. There are 2 exceptions. Really, there are 3. If it's O2, then it's pure oxygen. It belongs in the first one. So we don't consider that an exception. We consider that covered in the all atoms in elements. But the other 2 exceptions are when oxygen forms a peroxide, and that means when there's a double bond in here. So H2O2, hydrogen peroxide, lithium peroxide, sodium peroxide. In these cases, oxygen's going to have a oxidation number of -1, okay, instead of -2. And that has to do with the double bond that it has there. And then the last exception for oxygen is when oxygen is bonded with fluorine. So remember, when we looked at the electronegativity in the periodic table, fluorine had a huge electronegativity of 4. It has the highest electronegativity on the whole table. Next to it is oxygen, both in the periodic table and in electronegativity. Oxygen's electronegativity is 3.5. So when oxygen bonds with anything else on this table, it's going to have a higher electronegativity, except when it bonds with fluorine. When it bonds with fluorine, fluorine wins the electron. So fluorine gets the -1, and oxygen will then become a +2, okay, because fluorine will take the electron, and so it'll form OF2. It has to have 2 fluorines because fluorine has a -1, okay? For all of the other guys, whenever they form, when anything that's an ion, it's just going to have the charge of the ion. So all these dudes in the first column here, they're all going to have an electronegative or an oxidation number of +1, except for hydrogen. In the second column, +2. Okay? Over here on this end, most of these will have a -1 unless they happen to be bonded with something with a bigger electronegativity than them. Okay? So usually, if they're ions, then their oxidation number is just going to be the charge on the ion. So sodium ion, +1. Sulfur ion, -2. So it's just the charge on the ion. So then, the ones that that aren't clear, we can figure out. We can figure them out by assigning the common oxidation numbers to the things we know inside. Okay, let me stop using vague terms and let's do an example. So let's look at the first example you have down there, CH4. Okay? So CH4. So if we go back to our rules, it says that H4 has an oxidation number of +1. H does. And so then the question is, so what's the oxidation number of carbon? So if we call the oxidation number of carbon X, because we don't know it, then X plus, there's 4 hydrogens, 4 times a +1, has to equal the overall charge of this dude. And the overall charge of this guy is 0. It's a molecule, no charge. And so now I can solve for X. It's higher order math, but if I do this carefully, I should discover that the oxidation number for this carbon in this particular compound is -4. Okay, so the oxidation numbers of all the entities inside a compound, when you add them together, has to give you the net overall charge of that compound. So for CH4, the net overall charge is 0, so it has to add up, the oxidation numbers have to add up to 0. The other example you have there is MnO4. MnO4. And that is a complex ion, a polyatomic ion, and it has a charge of -1. So the question is, what's the oxidation state of Mn? Well, we know oxygen is usually -2, unless it's one of the couple of exceptions for oxygen, and this one isn't. And there's 4 of them. So if we call Mn again X, then it will be X plus 4 times -2 for oxygen. And this time, when you add up the oxidation states, they have to equal -1, because that's the charge on this compound, this complex ion. And so now we do the math. X minus 8 equals -1. Take the -8 over. X should equal 7. Okay? Let me do one more that's not on your sheet. Let's see. How about CrCl3, chromium chloride? Chlorine is in this column. It should have an oxidation number of -1. Okay? And so the question would be, so what is Cr? So if we call CrX, then it'll be X plus 3 times -1. Overall charge on this dude is 0. Okay? And so solve for X, it should be equal to 3. Okay, so that's how you do the oxidation numbers. Try the ones on the back of the sheet, and I'll post a video showing you the answers. Okay?